All right, let's analyze some motion graphs here. So I'm going to be using pen, although I normally recommend pencil, but I think pen just shows up a little better in the videos. So we've got this position graph, and we want to make a velocity graph out of it. So I always recommend labeling each distinct segment of the motion, A, B, C, D. And remember that position, velocity, and acceleration are all vector quantities, so direction matters. So we use positive and negative signs to show direction. So you can always just kind of think about the actual physical profile view. If you are watching somebody walk from a reference point, position of 0, just like a number line, the convention is to the right is positive, to the left is negative. It doesn't have to be that way, but that's the convention. So any position that's above 0 corresponds with a positive position. Any position below 0 corresponds with a negative position, and you can move either towards the positive direction or towards the negative direction. If you move towards the positive direction, even if you're at a negative position, you have to have a positive velocity. If you're moving towards the negative direction, you have to have a negative velocity. So with that little background, let's take a look at one segment at a time. Segment A, this person is moving towards the negative direction, or they're physically at a positive position initially, but they're moving towards a negative direction. So they have to have a negative velocity. And the next thing, if you look at the very beginning of segment A, their position graph is almost horizontal. Their position is barely changing. That means they're moving really slowly. But as time goes by, the rate of change of position or slope of this graph gets steeper and steeper and steeper. They're covering more ground every instant, so they're getting faster and faster and faster. So putting that all together, towards a negative direction getting faster has to be a negative velocity getting faster. So it's going to be like this. Do the best you can to line up your segments vertically for clarity. And this is a bit of a judgment call. If you think that the very beginning of segment A in the position graph is completely horizontal and their position doesn't change at all, that means in the beginning, velocity is 0. I feel like it's almost horizontal here, but the position is very gradually changing, so I start out with a velocity that was almost 0, but not quite. Now, if we look at the transition to segment B here, during segment B, going towards a negative direction, so you have to have a negative velocity. And unlike the last segment, this is linear. So that means they're moving at a smooth, steady, linear rate. Well, just like somebody walking, if you're moving at a smooth, steady, linear rate, that means constant velocity. And notice, look at the rate of change or slope at the end of A. It's really steep. They're going fast. The velocity is far away from 0. As soon as B starts, it instantly becomes a more gradual slope or gradual rate of change of position. So putting that all together, it's a constant negative velocity that's slower than it was at the end of A. So we'll do the vertical dotted segment to show that transition. And then once we get to C here, if we look at the very beginning of C, similar to the very beginning of A, although I would say this is perfectly horizontal, so at the beginning of C, their velocity is actually 0. And then the slope or rate of change is getting steeper and steeper and steeper. They're getting faster and faster and faster. So that's going to go something like this. And now if you look at D, it's a linear slope or linear rate of change that's more gradual than the end of C, but it's towards the positive, so it's got to be a positive velocity. But because position changing more gradually during D than the end of C, that means it's slower than it was at the end of C. So it's going to be like that. Okay, moving on to the next graph then. So this one here, where we have a velocity graph, we have to work backwards to position. So remember, we've talked about this. Anytime you go backwards, if you know the velocity of an object, that doesn't tell you where the object is. Like if I just told you, okay, a car is going 30 miles an hour. If the only information you're given is velocity, that tells you nothing about its position, about where it is. So when you go backwards to make a position graph, it doesn't matter where you are at time 0. It's impossible to know. So you just pick a spot and go with it. So I'm going to break this up into appropriate segments, A, B, C, D, E, F. And the reason I took this smooth, uninterrupted visual segment here and split up into A and B, you don't have to, but A are positive velocities and B are negative velocities, and we use positive and negative signs to show direction. So when you go from positive to negative velocity, you change direction, which is pretty significant when analyzing motion. So I like to break that up into different segments. So segment A, positive velocity that's getting closer and closer to 0. So that means you have to go towards the positive direction. You have no idea what position you're at. You could be at the reference point, you could be at a positive position, you could be at a negative position, but these are positive velocities during segment A. You have to be going towards a positive direction. If velocity is approaching 0, so you're slowing down. So that's going to look like this. Notice I picked starting at the reference point, but I didn't have to. I could have taken this exact same curve for segment A. I could have started it down here. I could have started it up here. And along lines of clarity, to help distinguish or show what parts of the graph match up, do the best you can to vertically line segments up. And then you can also put little notes about unique points like velocity equals 0 there. And when this nonlinear segment gets horizontal, the position doesn't change. That corresponds with the velocity of 0. So during segment B, negative velocity, so now you're going towards a negative direction. This person turned around. And the velocity starts at 0, but then it gets further and further away from 0. They're getting faster and faster and faster, so that's going to go like this. And again, without specific data, I happen to go a little bit past the reference point. That's unknowable. I could have stopped at the reference point. I could have stopped a little short of it. You don't know without any data. Now during C, that's a constant positive velocity. So that means at a smooth, steady rate, you're going towards the positive direction. So it's going to be like that. And then D is a constant negative velocity. Now, E's a little tricky here. E, if you look, this little bit here is a negative velocity, so you're continuing to move in the negative direction. But notice, as soon as E starts, it's instantly closer to a velocity 0 than all of D. So that means the rate of change as you're going at a negative velocity, so you're continuing towards the negative direction, it becomes more gradual. And then once again, when the velocity equals 0, that matches up with the graph getting completely horizontal. Now this is where a little explanatory notes might help. This is such a small little segment, it's hard to tell, perhaps visually, if I intended that to be nonlinear or if it's linear and just, drawn by hand. It's not really a very good descriptor of it. So I would put a note like E, excuse me, and then you could say something like NL for nonlinear. And then F is a positive velocity, so going in the positive direction and getting further and further away from a velocity of 0, so getting faster and faster and faster. Okay, moving on. Segment A, B, C. During segment A, going towards a negative direction, so it's got to be a negative velocity, and the slope or rate of change of position is getting more gradual, so you're slowing down, and it never quite gets fully horizontal here, so you never completely stop moving. So that would go something like this. During B, going towards a positive direction, so it's got to be a positive velocity. Notice the very beginning of B, that rate of change or slope is very steep. That corresponds with covering a lot of ground every instant, so you're going really fast. As time goes by, your position changing more and more gradually, you're slowing down, your velocity is approaching 0. And it never fully gets horizontal here, so the velocity should just get close to 0, but not actually hit 0. Again, do the best you can to line up your segments vertically. A, B, and then during C, you're going towards a negative direction, so you need a negative velocity, and it's a smooth linear rate of change, so that's a constant negative velocity. All right, here we go. Segment A, B, C, D, E, F. So a lot going on here. So during segment A, it's a constant rate of change, linear, so that means your position is changing at a smooth, steady rate, and your velocity is changing at a smooth, steady rate, but you're getting slower, and since you're getting slower and slower and slower, your rate of change of position is decreasing. And then B, for all of B, your velocity is the same as it was at the end of A. So I'll make up a number here. Let's say at the end of A, the velocity was 3 meters per second. Whatever your slope or rate of change looks like at the end of segment A, you need to continue that for all of B, because B's velocity is a direct continuation of what you were doing at the end of A. So that would go something like this. Again, no idea where to start at time 0, but just logistically, these first two segments are positive velocities going towards the positive direction. So to give myself room to work with, I'm going to start down here, so I have more space to go up the page here towards the positive direction. So here's segment A, and the rate of change or slope at the end of A, caused by this velocity of basically 3 meters per second, you're just continuing that velocity for B, so that's got to be a continuation. So I write something like linear continuation of the end of A. Then during C, constant negative velocity, so you're going towards a negative direction, a smooth, steady, linear rate of change. And then D, also a negative velocity, so you're continuing in the negative direction, but the velocity is approaching zero, so it starts to level off. And again, I'll put a little helpful note just to help for clarity of what the different segments are. Then during E, positive velocity, getting further and further away from velocity zero, so you're getting faster and faster and faster. There's E. And as soon as F starts, you're immediately going slower than you were at the end of E. So it's got to be a more gradual slope or rate of change of position here. But it's still a positive velocity, so you're still going towards a positive direction. So that's going to be like that. All right, let's jump to some graph trios now. So with this velocity graph here, I'm going to label my segments A, B, C, D. So segment A, a constant positive velocity. So you're going towards a positive direction at a smooth, steady, linear rate. And if I look at B, also positive velocity, continuing to go towards a positive direction, but you're getting faster and faster and faster. So keeping that in mind, I'll do segment A like this. And then during B, continuing to move towards the positive direction, but you're getting faster and faster and faster. That's going to go like that. And then segment C, now that you have a negative velocity, that means you turned around. And notice it's a negative velocity, you turned around, but the velocity is approaching zero, so you're slowing down. So you have to go towards a negative direction while you're slowing down. So that's going to go something like this. And it never gets fully horizontal there because the velocity doesn't quite hit zero. And then during segment D, also a negative velocity, so you're continuing to go in the negative direction, but now the velocity is going away from zero, so you're getting faster and faster and faster. So that's going to go like that. Now the acceleration. Acceleration is rate of change of velocity. So any horizontal segment on your velocity graph, if you think about slope, rise over run, if we picked any 2 points on segment A, there is no rise because it's perfectly horizontal. Your velocity is not changing. So that acceleration is zero. So just darken in the t-axis there. Acceleration is zero. During B, it's a positive velocity getting faster. So that means whatever is causing you to accelerate is working with your velocity. That's why you're getting faster. So we use positive and negative signs to show direction. Well, it's a positive acceleration. That would make a positive velocity get faster. During C, this is a negative velocity getting slower, so something's working against that negative velocity. Well, what would work against the negative velocity? A positive acceleration. And this looks a little more gradual than this one, so it should be slightly below it. And now this is a negative velocity getting faster because the velocity is going away from zero. Well, what helps a negative velocity get faster? A negative acceleration. And so another way to think about these acceleration graphs is each segment, acceleration is the rate of change of velocity. Well, we know in the graph world that phrase rate of change means slope. So you can literally just go through each individual segment and ask yourself the question, is the slope of this velocity positive, negative, or zero? And that'll tell you what the acceleration is. The slope of segment A is zero because there's no rise and rise over run. If the slope is zero, acceleration is zero. During segment B, that's a positive slope, positive acceleration. Segment C, positive slope, positive acceleration. And notice it's a little drop down because the slope or rate of change, even though there's no numerical values, we can visually see it's less steep than B. And then D is a negative slope. Anything sloping down the right is negative, so it's a negative acceleration.